Hello. Hey folks, welcome to part two of our lecture here about writing and balancing chemical equations. So we're going to start with looking at a chemical equation. Okay, here is practice exercise 520, and we are given a reaction represented by an equation. We have C3H8 gas, just propane, by the way, plus 5O2 gas reacts into 3 carbon dioxide gas plus 4 H2O gas. And just some identification questions here, right? Identify the reactants and the products. B, identify the coefficients. Explain what they signify in terms of molar ratios. Identify the physical states of each reactant and product. And how many carbons, hydrogens, and oxygen atoms are on each side of the arrow. And what does this indicate? All right, so go ahead and think about those for yourself. And when you come back, I'll go through them each individually. So pause and okay, welcome back. So the reactants and products, um, right, the reactants are everything to the left, so represented here in red, and the products are on the right side of the arrow in blue. And you can write them out separately if you wanted to. Now, what are the coefficients and what do they signify? So the 5, the 3, and the 4 are the coefficients. And then the hidden coefficient on propane, which is 1, right? And if it's 1, it's not there. So this would mean that 1 mole of propane reacts with 5 moles of oxygen to produce 3 moles of carbon dioxide and 4 moles of water. Any of those could be turned into what we call a mole ratio and used as a conversion factor. For example, I could say 1 mole of C3H8 would give me 4 moles of H2O. Or I could flip it. Or I could look at propane and CO2 or oxygen and CO2 and say maybe I would get 3 moles of CO2 for every 5 moles of O2. Okay, so any of these can be turned into what we call a mole ratio, and we will spend some time uh, looking at mole ratios a little bit later on, but we can hint at it already when we see the coefficients here. Okay, part C asks about the physical state, and so we can see in this case all of them are in the gas state as indicated by the G. Other options would be S for solid, L for liquid, and aqueous for dissolved in water. All right, and the last, how many of each type of atom are on each side? So if we look at carbon, we have one molecule with 3, so that gives us 3, and we have a molecule, 3 molecules with 1. So right here, 1 times 3 turns into 3 times 1, but we still have the same amount. So all 3 of those carbon are in one molecule in the reactants, but once we get to the products, they split into 3 separate molecules, each with 1. So that's kind of how we can think of it. And water, or sorry, hydrogen, right? We have one molecule with 8 hydrogens. It turns into 4 molecules, each with 2 hydrogens, which gives us the same amount. And oxygen, we have 5 molecules with 2 oxygens each, turns into 3 molecules with 2 and 4 molecules with 1. So all in all combines to 10. Everything has to be accounted for, indicating that no atoms have been created nor destroyed during this reaction. Okay, so far we've given you balanced equations, but what if we have one that has blank coefficients and we want to balance it ourselves? We're going to follow some guidelines for how to do this, and using a combustion reaction is a good start. So the first step is we look at our reaction right? And we have everything here is accounted for. We have our reactants, we have our products, and it's not currently balanced. So first thing we want to do is balance one atom type at a time. And there is kind of a strategy to this. We want to start with atom found only on one compound on each side, right? So for example, um, oxygen, right? See, oxygen is here in two different molecules, and um, so we want to save that for later. Also, another key, oxygen is by itself right here. So whatever we end up with oxygen at the end, if it's not balanced, we can simply adjust this one without messing anything else up, right? But if we change hexane, this is hexane by the way, then we change carbon and hydrogen, right? Or if we change water, we would change hydrogen and oxygen, and CO2 would be oxygen and carbon, right? So ultimately at the end, we're gonna use this to correct oxygen and balance everything. So let's start with carbon, and we have 6 carbon on the reactant side right here, and 1 carbon on the product side. So if we place a 6 in front of the CO2, we now have this balanced carbon. Okay, next step. Uh, well, we want to insert whole number coefficients before the formula. So we did that with carbon. Now we want to balance H, right? And so if we look, we have 14 hydrogens on the reactants. We have 2 for every water molecule. So how many waters do we need? What should we do for H2O to balance this? I guess it's already there, right? If we put a 7, we now have 14 hydrogens um, on the product side. So now carbon is not affected. Hydrogen is now balanced. And the last thing is to look at oxygen, right? Also, here's a good point. Never change the subscripts in the formula. We just add coefficients, as we said before. So now oxygen is kind of like the cleanup, right? So we can look at how many oxygens we have. And here we'd have 12, and here we'd have 7. So we have a total of 19. And so if we have an O2 molecule, we would need 19 halves of it, right? Well, that's a bad 19. We're going to keep it as a fraction for now. So we would need 19 halves of O2. However, remember we want whole number coefficients. Whole number coefficients. We want to get rid of that 1/2. And we can do that by, here, let me clean up this. Okay, so if we can multiply the whole thing by 2 to turn the fraction into a whole number, which then gives us, well, yeah, there's her answer. And then now it gives us whole numbers. So we have 2, 19, 12, and 14 instead of 1, 19 halves, 6, and 7. All right, so this is a good example of all the steps. If you end up with a fraction, multiply the entire equation to get rid of the fraction. And here is confirming that everything is balanced. Now I will note that this here is balanced, right? It is balanced if you went through the work of adding up all the atoms, and you even have whole numbers of atoms. But the last step is we want to make sure we have whole numbers of molecules. And so that's why we would multiply again there. Okay, let's do another one. Okay, another combustion reaction. So we're going to follow similar kinds of steps, right? We have C6H12O2 plus oxygen, O2, reacts to form CO2 plus H2O. Sorry, that gas looks like it. I ran out of room, so it should go there. Okay, so remember, first step, we want to balance which one? We want to balance carbon, right? And so looking at what we have, first we would put a 6 in front of CO2, okay? And then what did we do next? We wanted to balance hydrogen. So we're going to count up hydrogens that we have, and we see that we would need to put a 6 in front of H2O. And now we will balance oxygen with the remaining, the last thing. So this one's a little bit different, right? Because we already have, we have 2 oxygens here, right? So we have 2 on this side, and over here we have 12 from CO2 plus 6 from H2O. So we have 18, and we have 2 already over here, so we need 16 more to balance out, which means we would need 8 O2, right? So if we put an 8 in front of O2, now everything is balanced. And so that's final answer. We don't need to multiply because we don't have any fractions or anything. Everything is whole number ratios, and you can confirm for yourself that there are indeed the same number of each type of atom on both sides. All right, balance this equation. NH3 plus O2 forms N2 plus H2O. So it's a little bit different, but similar, right? We still have reactant plus oxygen. So let's just go ahead and pick one to start with, and maybe we can start with nitrogen. And we see that to balance the 2 here with the single NH3 here, we can put a 2 in front of ammonia. Now let's look at H. What do we need to do for H? If we have a 2 here, we now have 6 hydrogens, and so that means we need to adjust this one to put a 3. So you see how each step influences the next. Okay, now let's balance the remaining, all that's left is oxygen, right? And so we can see that we have just 3 oxygens on the product side. And so we're going to need 3 halves of O2, right, to balance it out. And now we once again face the problem of a fraction. So multiply the whole thing by 2. So we double all the coefficients, and we now have a balanced reaction of 4 ammonia plus 3 oxygen makes 2 nitrogen plus 6 waters. Okay, we're going to stop here for part 2, and when we come back, we'll talk about stoichiometry, which is looking at those mole ratios again using balanced equations.